Okay, so here we go. Now, we know he jumped 8.9 meters just for our American sensibility, and my apologies to those of you who didn't grow up in the United States and are taking this course. To you, to those students, 8.9 meters makes perfect sense. I mean, you got a feel for it because, from a sophisticated country that actually uses the darn metric system, which is into tenths and not sixteenths and fourths and pounds and ounces and silly stuff like that. But anyway, go ahead and convert that to feet. You can Google that. Okay, let's go back to the 8.9 meters for the range of the jump. Actually, that was where his feet hit, and then due to his extraordinary, he was able to flip his center of mass up over his feet before his backside hit. Okay, so his feet hit at the 8.9 meters, but his center of mass did not travel that far. All right, his center of mass did not travel that far. As a matter of fact, his center of mass is forward, and that's the other thing too. His center of mass might have traveled that far, but when he took off, what are you trying to say, Professor Riggs? Have you lost your marbles? Here's what I'm trying to say. When he took off, he was running along, okay, and when he's taking off, now he's over his center of mass is over the starting line. All right, and still with this extraordinary ability. So his center of mass did not travel 8.9 meters. His feet did, but using our equations, we have to use the center of mass. Clear as mud. All right. Okay. All right. We're calculating how far center of mass travels. So according to an article in Wired magazine, and I kind of re-engineered, and I had a quibble with one of their calculations that analyzed this jump. Beeman took off with an initial velocity of 10.1 meters per second. That's at an angle of 26.5 degrees. Well, so much for that optimum of 34 degrees. He took off with and for his body type and all that, that was probably his optimum angle. I mean, you can't get any better than the jump that he did. So, what was Beeman's speed in the X direction? Now, we've done that. If you want a quick review of it, here we go. So, if we have his velocity, his initial velocity was 10.1 meters per second, and he launched that at 26.5 degrees. Then v naught x, his initial velocity in the x direction, which never changes because that's not where the acceleration is equal to 10.1 times the cosine of the angle. All right. Okay. Hopefully, I know every calculator out there has a cosine function, and I know that if you don't have that, then on your computer you can do it. You can find a calculator that does that. All right. So what's his initial speed in the y direction? Let's review that one. Let's review that one real quick. So his initial speed in the y direction. So we did this vector. Now we're doing this vector. Initial speed. I'm kind of hoping that some of you that are taking this class that had me for Physics 210 and 220 are going, Professor Riggs, you should teach projectile motion using Bob Beeman's jump. Then everyone would get it. I think you're right. Instead of using the stupid textbooks that we use, yeah, I think you're right. Sine of the angle. Okay, good. Now, using Beeman's velocity in the y direction, calculate the time he was in the air. Remember how we did that. I'll give you a quick review. Here it was. Because we know that his final velocity is equal to his negative of his initial velocity in the y direction. And so you go negative initial velocity in the y direction is equal to the positive initial velocity in the y direction minus 9.8 times t. Now all you got to do is solve for t. What happens when you subtract this from both sides? you basically get this. Negative 2 V naught Y is equal to negative 9.18. That's as far as I'm going to go with you. All right, you can get it from there. Because we've already done that before. Okay, now that we know the time in the air and his speed in x direction, calculate his range. Remember? And then convert your answer in 19 to feet down 20. So that's easy. All right, so calculate the range. Let's look at that real quick. Range is equal to the V naught x that you got up here times the time that you got right here. You guys have done some hard ass physics. I'm just going to tell you. Good for you. And if you follow this, you're like, hey, I can do this. That's right, you can do this. Comfort of your own dorm room or your own apartment or whatever, just taking your time. Yeah, you got this. All right, so let's go on to the last question. Convert that to feet. Now, okay, let's do one simplified problem for the high jump. We're going to run. We're going to take a 65 kilogram female high jumper. And basically I took the 1.9 meters, which was the video I showed you of the woman from Spain who won the 2016 high jump. Took her height that she won with, and we're going to convert this. So on problem 21, here's what that looks like. You're going to have, she's going to be doing her run up. You know, she's going to be running up, so she's going to convert that kinetic energy, which is equal to 1/2 mv squared, into her potential energy, which is mgh. All right? So a nice thing happens here. The masses cancel. So it works out the same way as if it's as if she fell 1.9 meters. There you go. There's the equation. Now, don't forget, all of this goes in first. Then you take the square root. Okay, have fun with this. And then we'll do home runs. Now you're ready to do home runs, and it'll be fun. And it'll go so much quicker because we've already laid the groundwork.